Hi there, and welcome to the DynamoDB corner of the Amazon Web Services YouTube channel. I'm your host, Sean, and I'm coming to you from Dallas, Texas, just like the other videos you may have seen, but this time we're focusing on the history of DynamoDB and how it works under the hood. I will be the primary presenter for today's topic, so please let me tell you a little bit about myself. I've been with Amazon Web Services for a decade, and since the first year, I focused on DynamoDB, beginning in AWS Premium support, and now for the last 7 years as a solutions architect for DynamoDB. I've helped unicorn-sized startups, enterprises, and businesses of all sizes be successful on DynamoDB. And as the most tenured DynamoDB SA, it seems fitting that I get to present the history of DynamoDB. Grab your drink of choice, lean back, and get ready to learn.
Let's talk about DynamoDB's history and how it works underneath the surface. My name is Sean Schreiber, and I am a senior DynamoDB solutions architect. I've been with AWS for about 10 years, and I have focused on DynamoDB for the last 7. In my role, I work with businesses of all sizes, from small startups to unicorn size startups to enterprise companies, and I use all my experience to help make them successful on DynamoDB as they move new workloads to the service, try out new features, or in cases like with Disney, continue to grow on the service as their customer base grows. So DynamoDB is a very popular service, and we're going to discuss where it came from, some of the history of AWS that comes all the way back from 2007, which kind of shows up a little bit in the DynamoDB service that we use today. And then we're going to talk about how is it built, what are some of the services underneath, and of course cover some of the basic features. Here's the agenda so you know what we're going to be covering today. Sometimes we wake up in the morning and we ask, why NoSQL? Just kidding, but I'm going to try to work some dad jokes in here, keep it interesting. But why NoSQL? We want you to understand the importance of NoSQL databases, how they, of course, are here to stay, what workloads work well on NoSQL databases. Then we're going to make sure you know all the keywords about DynamoDB, tables, indexes, that kind of thing. And yeah, this is going to be about a 200 level presentation. So if you're brand new to Dynamo, these are a lot of new concepts. This should be great for you. And if you already know about Dynamo, you're developing code on top of Dynamo, this may be a little boring, but please stick in there. We are going to cover a lot of ground. So as I mentioned, Dynamo really kind of started, way back in Amazon's history. We can talk about the Dynamo 2007 paper, which describes a database called Dynamo, which is not DynamoDB. It's Dynamo 2007 is much more like Cassandra, but we can even rewind back to December. Remember we had to do that with VCR tapes. December 2004, with the database scalability challenges that Amazon had. They had a multi-hour outage in December of 2004. It's a peak time for sales for Amazon.com, and the root cause is they had a fully configured, sharded database. However, even though it was configured as it should have been, there was just more traffic than it could handle. And we scaled beyond the capabilities of that relational database. So our response was the Dynamo 2007 white paper. You can go ahead and read it. However, if you're going to read any white paper, if we skip to July 2022, I'd say check out the DynamoDB paper. It kind of explains a little bit of how the service works underneath the surface. Now, Dynamo is an old service in a way. I mean, it's not a teenager yet, but as of the recording here in 2023, it has been around for over a decade. And we've seen a lot of features come since it originally launched. We now have on-demand, we have adaptive capacity, we have auto scaling, backups, point-in-time recovery. What I like to say about features for Dynamo is if you need it, we probably have it. It's probably already part of the service. Perhaps maybe if you want something really, really unique, it might just be in the roadmap. But for that, let's talk to your account team. Now, so today, DynamoDB is a tier 0 dependency, and that means that if that service goes down, other things break. So if DynamoDB were down, you couldn't check out on Amazon. So think about it. When's the last time you tried to, but were unable to buy something on Amazon.com? Hopefully that's a really, really long time ago, or it's never happened. So that's what we mean by Dynamo being a tier 0 dependency, tier 0 service. It's used by so many services inside of Amazon. Now, over time, we see that cloud applications, cloud native applications move to the cloud, have a massive amount of volume and bytes in traffic, in IOPS, like disk access, like, kind of connecting to Dynamo's provision capacity mode with WCUs and RCUs, if you knew about that. And performance requirements are just increasing in standards. Like, it used to be that we could go from, to milliseconds. That would be fast enough. Now we need microseconds. It seemed to be that people cared only about the average latency, and now like P99 or sometimes even 4 nines, that percentile, 99.99, that's what matters to our customers. And so there is a race to get these cloud native services like DynamoDB to be faster, to handle up to petabytes of data. And this is kind of the drive behind the creation of DynamoDB. If you look at the Dynamo 2007 white paper and compare it to DynamoDB today, you can see how DynamoDB made some opinionated decisions. We made the service that could scale horizontally by adding in servers, but we'll talk about that in a little bit. So here's what you get with a distributed database like DynamoDB, which is fully managed. You have no servers to provision, to benchmark. You see here a spike in traffic. This was the Super Bowl, and the consumed capacity went from millions, 2 to 4 million capacity units, all the way up to a spike of over 10 million WCUs. And that's pretty amazing. And the cool thing about this is this customer did not have to inform AWS of this spike in traffic. So long as you have an account limit that is sufficient, you can do things like this. Now, if you see, there was an overconsumption of capacity where they use more than the provision, and that's because we have burst. So even in our provision mode, which was still very popular, if you try to consume above your provision, there's some allowance for that using our paid for but unused capacity, which is our burst capacity. But we'll talk about that a little bit later when we go under the hood. And so as customers send us traffic, we see the latency goes down, lower latency for higher traffics. This is kind of counterintuitive, but for a service like DynamoDB, it makes sense. It allows us to cache information like your encryption keys, your credentials, and all those great pieces of information. And so for customers who need that low latency, consistent latency, and they like the scalability of the service, one of the hard challenges is getting your data into every region. And so that's where our service, our subservice called Global Tables, comes into play. Global Tables is a fully managed multi-region, multi-active database. And it's not easy to build, but we have made it. It's actually now in its second iteration with Global Tables 2019. 1121, I believe, is the technical name of it, aka also known as Global Tables v2. Global Tables uses a last writer wins conflict resolution strategy, and we use a timestamp to do that. When you write data into a DynamoDB table, you're interacting with a region, a regional endpoint, and then we apply a timestamp at the storage layer to that item change and then replicate it worldwide. Global Tables is kind of like an anti-entropy machine. We want every replica to have the exact same copy of the item, so we replicate that as quick as we can. Now, with Global Tables, you have access to our availability SLA, which gets you up to 5 nines of availability. And we also have an SLA just for, regional connections. So do check that out. On our page, you can kind of search for it. It's just DynamoDB SLA, and there's all kinds of very specific terms and ways that SLA is calculated. If you really look at SLA, it just provides a service credit if the error rate in the account is high enough. But just remember that something like DynamoDB, even in just one region, highly available, trusted by companies such as Snap and Disney and Netflix. So now let's say you have a customer, maybe this is you, and you need to get latency down to microseconds. That's where DynamoDB Accelerator or DAX comes into play, DAX. We like to say it's a 10 times increase in latency because what we're doing is taking your reads from 4 milliseconds down to 400 microseconds. Now, that's not a guarantee. Do test it, run your code on it, and of course, your item size plays a big part in whether we'll be able to return your items back in under 1 millisecond. But this is a great service if you have a data set that maybe doesn't change very much, that needs to be read very, very quickly, meaning you have a very tight SLA. So what I like to say is if you have like a product catalog. Product catalog is a great use case for DAX because there's a lot of items, but it's probably not in the terabytes. It doesn't change that much aside from perhaps price. And there's a lot of popular items that need to be read out. And DAX is going to be really great for that subset of data that is very frequently read. Now, DAX is great for developers so long as your SDK is supported, and it's in pretty much all the popular languages. You can access it in Java, JavaScript, .NET, for example. You can go check our documentation for the currently available SDKs, but it's API compatible in that as a developer, you just change the SDK that you import, and you just, it uses the DAX SDK uses the same interface as the regular DynamoDB SDK. So there should be few code changes, not many. And then all of a sudden, all your requests are going to DynamoDB Accelerator, which sits inside of your VPC. Now, taking a step back to the 10,000 foot level, what do you need to know about DynamoDB? Well, it's probably pretty clear at this point. DynamoDB provides consistent millisecond latency. It is designed to be an operational database and to be very, very quick at what it does. It's also highly available. We keep your data in 3 different availability zones. So for that reason, it is designed for mission critical applications, in particular OLTP. So if you really need a predefined query, as long as we can structure your data to match, a kind of NoSQL access pattern, which we'll talk about here in a little bit, you're going to be able to go to millions of requests per second. And as I mentioned earlier, DynamoDB has all the features you expect. We have encryption at rest, global replication, we have SLAs, we have no downtime upgrades. The service is always being updated all the time underneath the surface, and you can't see that. We have 2 capacity modes, provisioned or on demand, so you can either pay for each request or take a guess about how much capacity you need and pay for it every hour. And then we have all the integrations you need with the AWS ecosystem. So do you want your records to go to a Lambda function, your CDC data to go to Lambda function? You can do that. Do you want it to go to S3? You can do that with Kinesis data streams. We have an integration with KDS where we'll publish your record changes into your KDS stream. Do you want to export all your table data to S3? We can do that. Point-in-time recovery to 1 second in the last 35 days, we can do that. Cold backups, we can do that through our AWS backup integration. So we could go on, but the takeaway is that DynamoDB is an enterprise-ready NoSQL database. It is fully managed. It's highly scalable, trusted by major enterprises and companies, including Amazon, and of course, companies that definitely resonate with you. For example, if you go and open up your Disney Plus account and you get a recommendation of what to watch next, that comes from a DynamoDB table. There was a talk on that at reInvent. So if you look for Disney Plus DynamoDB on YouTube, you should be able to find that. Now, we've talked about NoSQL. Everyone has their own idea of what NoSQL means. Some say it's NoSQL, like don't have any SQL, the programming, the coding language in there. Some say NO stands for not only SQL. What we're trying to say is that, NoSQL data is really kind of how we define a NoSQL database is it is for denormalized hierarchical data with instantiated views that's designed to scale horizontally. And so, by the way, not all NoSQL databases really will scale horizontally. And then built for OLTP at scale. So, low latency puts in gets. Now, what does OLTP at scale mean? So, for example, shopping carts or session services for millions of users during a huge sale, such as Amazon Prime Day, that's where an OLTP at scale database such as like DynamoDB can come into play. And another way to consider like is a workload OLTP you can think of predefined access patterns, because in NoSQL databases, we could create these aggregations, aka these instantiated views where we're kind of collecting data together under the same key. And so if you have 90 to 95% of your access patterns that are kind of predefined, we can get that into a NoSQL database such as DynamoDB. Now, the ad hoc queries, we can solve for ad hoc queries, but we have to bring in other solutions. Like, for example, you can export your table data to S3 and then query it via Athena. So we have a native export to S3 feature. Now, with NoSQL databases, you start with one node, and that's your building block. It's just the first one. So services like DynamoDB just start with one node. Now, with a traditional SQL database and RDBMS, we are going to scale by increasing the node size. However, NoSQL database is scaling horizontally. So NoSQL delivers on the promise of a massive scale by using horizontal scaling, where data and workloads are partitioned over a number of shards that can grow as the data volume and throughput grow. And scaling is incremental, which means more nodes and partitions are added as needed. Nodes are inexpensive commodity hardware. They bring in CPU, memory, network bandwidth, and are understandably a very good thing because it's going to let us achieve high levels of throughput. Now, if you build this NoSQL service correctly, you do it right, the performance does not change as the data and throughput grow. Performance at scale was one of the main goals for NoSQL databases, and that is certainly true for DynamoDB. Now, there's two things that you need for this to work. You need to have the technology to be able to do it, and AWS does. And then the user has to have a good partitioning scheme. You need to have a good schema. And we'll kind of touch on that. The schema is really under your control. We want to make sure that you're not pushing too hard on one server in DynamoDB, which we'll call, we really call them storage nodes. We'll get into that later. And let's talk about kind of what happens underneath the surface. So you see tables, okay? And, DynamoDB is a multi-tenant service. So we put multiple tables on the same servers, we call them storage nodes. And technically speaking, we create partitions. So you see tables. Underneath that is one or more partitions. With on-demand tables, it's at least 4 partitions to begin. Each partition is a section of your data. It's a slice of your key space. So, let's say you have 4 partitions. In theory, on an on-demand table, it means that each of those has 25% of your data. Really, it's technically 25% of your key space, but it's really up to you as the schema creator to evenly access those partitions and make sure you don't try to load too much data onto one partition or another. Now, you can certainly write more data, but be aware of the limits here in DynamoDB. So the limits are 1,000 WCUs and 3,000 RCUs. So a WCU is 1 kilobyte and RCU is 4 kilobytes with strong consistency. So you can't push a single partition, one slice of your data harder than that. Now, put another way, you can't read or write to an item, which is synonymous with a row, at a greater rate than 1,000 WCUs, or basically 1 megabyte per second, or read it out at 3,000 RCUs, which is about 12 megabytes per second. Those are kind of our limits, and that's our fundamental limit that we work backwards from as we design NoSQL schemas. But this is not a NoSQL design presentation, so let's talk more about horizontal scaling. So essentially, you have a workload, and you are writing data in. So there's bytes, there's read units, write units, data's flowing in. It has to be stored in bytes on disk. And what we do on the DynamoDB side is manage servers for you. We bring in more storage nodes. We make new partitions as your data comes in to respond to traffic. Now, there's a couple ways that this is done. One, in the provision mode, we add capacity as you request it, or as the application autoscaling service requests it on your behalf. Or with the on-demand capacity mode, read and write capacity management is fully automated, and you simply pay for read and write requests that you make. Let's get some common terminology down. Let's discuss DynamoDB tables before we get too far into the conversation of the DynamoDB service. So, tables. Data sits inside of tables. A table holds your data. A table is unique in that given account ID and a region combination. A table name is a string literal, so you could call a table like accounts or bookmarks or driverless cars or whatever. Now, DynamoDB data sits inside an item. Conceptually, it is similar to a row. It is an atomic unit of data, and all operations on items are ACID. Really, I should say all operations on single items are ACID. Now, if you want to do multi-item transactions, you have to use our transaction API. Now, all items must have, there's attributes. All items must have partition keys. Partition keys are attributes, by the way, as are sort keys and A3 and A4 and A5 and all the different A's that you see here. Those are known as attributes. So partition key is also known as a hash key. The partition key is important to find your data. Now, without the partition key, we don't know where your data is. And we'll look at how data is organized here in a bit. Now, in DynamoDB, it's super important that you know what that partition key is. Now, the partition key could be something you derive, or it could be a set of values, such as a number between 1 and 1,000. It's important that when you choose your partition key, though, it be significant. It be part of your application. Anyways, now let's talk about sort key. Optionally, you can have a sort key. A sort key allows for one-to-many relationships in DynamoDB. Sort keys are often things like timestamps, version numbers, or audit log IDs. The sort keys are used to create groupings of data. Sort keys are used to sort data on disk, which I would say is a good name for them, sort keys. And they're also called range keys. If you look at our API, you'll see them called range keys. Now, this opens up a lot of query patterns where you can request a range of rows to be returned under a partition key using a between statement on the sort key. Now, when you have a table with a partition and sort key, the two are collectively your primary key. Combined together, the two uniquely identify a single row in DynamoDB. So, if you give DynamoDB a partition and sort key, we know precisely which row or item you are referring to, because row and item are kind of synonymous. But, in the APIs, they're all called items. You're about to see our API operations here in a little bit. So, let's look at some of the data types for a DynamoDB table. Now, we have a lot of what you expect: strings, numbers, binaries, bools, lists. You can do lists, you can do sets, sets of strings, sets of numbers, sets of binaries. So, lists are, ordered, and sets are basically, you can only have one of anything. So if your status was new and you put that into string set, you couldn't have more than one new. And then you have maps. Maps are like JSON documents. Now, take a look at here. Is there any attribute that you're looking for that you don't see? Now, the answer that people usually say is date or date time. So we tell our customers to store dates as a string data type. You could also do number, but it really depends on your use case. But if you do a string data type, use the ISO 8601 format. There's subreddits. If you are familiar with Reddit, there's subreddits for ISO 8601. And they're very adamant on how to use it. It's a specific standard, but also very loose. There's a Wikipedia page if you want to look for it, ISO 8601. But basically it goes from the least specific part of the date time to the most specific part. For example, the year will go first, and then the very end will be like microseconds, perhaps followed by time zone information. Now here's some of the API operations in DynamoDB. These are the ones that allow you to write data. We have singleton operations like put item, update item, delete item. So put item, put a new item in, update item, maybe update one attribute on an item or replace all the attributes in the item, except the partition key. You actually can't update a partition key or sort key for that matter on DynamoDB because those are the row selectors. If you're trying to change those keys, what you're saying is another item should exist with these values that I'm providing you. In that case, you do need to just insert a new item. So, fun fact. You can't update primary keys in DynamoDB. The values are set. You have to say, delete the old item and insert the new item. And you can do that with either the batch API or the transact write items API. So the batch write item is going to let you do a lot of like a delete and an insert. It won't let you do updates. So you can't say set the order status to in process. You cannot make that command with batch write item. You could do that with update item, however. So batch write items are going to let you either insert new items or replace them or delete them. Now, transact write items is pretty cool. So it's a transaction API. So you can do operations on up to 100 items in a single atomic operation. All will succeed or all will fail. And, there's also no locks per se, meaning like there's no blocks. However, if you're doing a transact write item call, and then later you come in and you try to update an item that's part of that transaction, that update could have a failure if it's trying to conflict with the transaction. That could create transaction confliction exception. So we do have ways to maintain the integrity of those transactions, but potential of conflicts. Now, those are all resolved on runtime, and it's a really cool API, but we're not going to go too much into it right now. Now, for your read operations, we have query and scan, which both return up to 1 megabyte of data. Query is very powerful. With query, you only need to know the partition key. You don't need to know the sort key, and you can get back thousands of items at a time. Now, the scan API is kind of like exporting data. It's used for ETLs or sampling. With scan, you don't need to know any primary keys. No partition key, no sort key. You can't really provide them. You can always use filters, but it's not supposed to be used for, critical OLTB operations because scans take a long time and they're very resource intensive. And be aware that whether it's transactions or queries or scans, these operations are done in milliseconds, tens of milliseconds. There's no like long running, queries here. These always come back super quick. Then we have GetItem or batches of GetItems, and then we have transact GetItems. So transact GetItems lets you create a get call. You can get up to 100 items at once, and it's going to let you retrieve really anything from even a group of tables all at the same time in that region. And so transact GetItems is paired with transact write items to handle conflicts. But how that works is a little bit out of scope for this 200 level presentation. But those are read APIs. It can be that simple. But if you want something that's simpler, that's easier to get started, look at Particle. Particle is a SQL compatible query language that allows you to select, insert, update, and delete data in DynamoDB. Using Particle, you can easily interact with DynamoDB tables and run ad hoc queries in the AWS Management Console, the Nosql Workbench tool. It's a client-side tool available in Mac, Windows, and Linux. It's like a GUI. Or the CLI, and of course you can use all the DynamoDB APIs to run your Particle queries. Now, Particle operations provide the same availability, latency, performance as the other DynamoDB data plane operations. It's really great. At the end of the day, SQL compatible query language lets you query across multiple data stores. And there's things that you can do with Particle that you can't necessarily do with regular operations in DynamoDB. So for example, if you want to set the order status to in progress on, tens of rows, you can actually do that with Particle, but you can't do that with batch write item. It allows you to do updates of many items all at once. So it's really great, but be aware that Amazon, two things, that Amazon DynamoDB supports a subset of Particle query language. Check our documentation. It's not the full, because Particle is an Amazon. I believe it's backed by Amazon. It's an Amazon query language. So that's the first thing. The second thing is, we're not allowing you to do joins. If you're familiar with what joins are, that is kind of antithetical to NoSQL databases. So we're not going to allow you to join rows together. We're still working with item collections, which is small subsets of data that you create in order to satisfy your queries. The high level view on how you should be structuring data in Dynamo is it's based on the access pattern. So, we'll get into that when we talk about NoSQL designs and how to structure data in DynamoDB. But something you're going to need to know to structure data in DynamoDB is what a global secondary index is, or GSI. GSI allows you to have an alternate schema on your DynamoDB table. GSIs are actually DynamoDB tables underneath. However, when you go to the AWS Management Console and you go to your Dynamo table, you won't see your GSI listed next to your other tables. Instead, they're under the Indexes tab of your DynamoDB table. So what makes GSIs unique? Well, only DynamoDB can write to global secondary indexes. DynamoDB is responsible for copying data from your base table into your GSI. Because this is a separate DynamoDB table, it is asynchronously updated. So to put it another way, GSIs can be kind of stale, kind of behind the base table, on the order of milliseconds of staleness, but potentially more depending on the situation. So the most important thing that you can do when you create your GSI is to make sure that you have enough provision capacity and you have a good schema for the table. You can choose whatever arbitrary schema you want, but remember, these are really DynamoDB tables. So you don't want some low cardinality order status as your GSI partition key because DynamoDB uses that partition key to figure out where your data is going to be stored. And if you're inserting 1,000 orders per second with the status of new, I love my order statuses. This is Amazon after all. That's all going to the same DynamoDB partition on the GSI. So be aware of that. Now, you can have up to 20 GSIs per table. That is a soft limit. We'll touch on that in a little bit. Oh, and by the way, whenever you construct these indexes, you can choose whether you copy just the keys, meaning the primary keys of the base table in the index. You can choose whether to include attributes by name, or you can choose to project all attributes. So keys only, or specific attributes to include, or all. Now, there's another type of index called an LSI. So LSIs are infrequently used. Now, LSIs are co-located on the same base table next to the rest of your data. So the benefit of that is the data is updated immediately with strong consistency. So you could write data into an LSI or to your base table. It's immediately reflected in the LSI. We copied over, and then you can do a GetItem with consistent read set to true, and we'll get you the most up-to-date copy of that item. So it's really helpful in that way. Now, whereas with GSIs, you can have arbitrary schemas. With LSIs, you really can only have an alternate sort key. So here you see, you still have to know what the PK value is. PK is partition key in A1, but you can choose to have A3 as a sort key. So it could be the last time the device checked in. It could be the firmware version. You have a lot of options with what the sort key could be. Now, common misconception in Dynamo is that partitions are quote unquote limited to 10 gigabytes, and that's really not true. So this misconception comes from LSIs. So for each partition key value, the total size of all index items must be 10 gigabytes or less. So for example, if you have a device model as your partition key and you have an LSI on firmware version, you can only have up to 10 gigabytes of items with the same device model number before you exceed this limit. And if you want to monitor that limit, you can request the return item collection metrics with your put item call, and it will tell you the approximate size between a set range, such as 8 gigabytes and 9 gigabytes, so you can monitor the size of the collection. Now, be aware LSIs can only be made whenever the table is created, and you're limited to 5 of them. Now, of course, DynamoDB does have a desired size for partitions. It is around 10 gigabytes. However, that's not what we would call limit. The limit of data under one partition key only applies in the event of an LSI, because I have customers that have 40 gigabytes of data under the same partition key. They can do that so long as those items aren't copied into an LSI. So here's a comparison of the two. Essentially, when you should use an LSI is when you need strong consistency. Otherwise, you can use a GSI. Remember, GSIs are eventually updated. They're milliseconds or even seconds behind, potentially longer depending on the situation. So GSI is preferred in almost all situations. And, you don't have the same limits. You're not going to be limited to an item collection size of 10 gigabytes. Plus, you can create and delete the GSI at any time. Now, let's say you're making your get items, your put items, your create tables, update tables, you're adding indexes, you're doing all these crazy things. What does DynamoDB underneath? What is it doing underneath? How are we flowing the items from the front end of the service to the storage node? How are we retrieving the data from our storage nodes, which are our storage layer, back to you? Maybe how do we handle consistency? Let's talk about that. Get under the hood of DynamoDB. So how do items work in a table? Now, items are inserted, and when you insert them, we hash the partition key. That's why in their API, those partition keys, such as order ID, we used to call those hashes. I mean, still called hash in the API, but in the documentation, it calls them partition key. So here we have different orders. These are rows, right? But we can call them aggregates if we want. And so DynamoDB breaks up our tables into partitions, one or more partitions. And, this hashing algorithm that we use, so we're going to hash one, and we're going to figure out which partition is responsible for that. So the key space is broken up between this fictitious range of 0 to FF. And when we hash the number 1 in our hashing algorithm, think of like a SHA-1 or something, the output, the digest of that would be like 7B. And 7B is between 55 and AA. This is hexadecimal. Yay, this is fun. And so that's how we know where that data goes. And so when we look at your next item, we hash that. That's going to end up in 48. Hash the third value, CD, it's going to end up in partition C. So important thing about hashing algorithms is that even if you change 1 byte, 1 character in the hash, aka the partition key, the item's digest, the output of that is going to be totally different because the outputs of these hashing functions are pseudo-random. That means that by just changing 1 byte, such as saying order 1, order 2, order 3, you are going to have outputs that are randomly distributed over the underlying virtual partitions. And of course, that's just as the number of hashed values approaches infinity, it appears as a random distribution if you're familiar with statistics. But yeah, hashes are super important. Now, an efficiency thing for you is to consider storing aggregates under the same partition key. That way I can say query for order number 3 and I can get the basic order information, I can get the rows, I can get the product information. If you structure your data in a good way, we can do one query and get a lot of different data back. Order history, product information, shopping cart info, all related to that order. But we're getting a little bit ahead of ourselves and talking about NoSQL design, Sean. Let's try to stick here and talk about this problem from a different area. So as we mentioned, DynamoDB data is replicated across 3 availability zones. So let's take order ID 1. We're going to hash that, and it's going to fall on partition B in AZ2. Now, in DynamoDB, we replicate data to 3 different AZs. So we're sending it to partition B and AZ2, and it's also replicating to the same partition, different copies of an AZ1 and A3. So here we have 3 copies of your data. Now, let's look at the architecture and how this looks from a server standpoint. So the DynamoDB service is composed of thousands and thousands of servers, but from a request standpoint, there's really 2 primary fleets. There's the front end, which is request routers, and the back end, which are storage nodes. Request routers, or RRs, as you see on the left side of the slide, are stateless, and they route incoming requests to the appropriate nodes in storage layers. And then storage nodes are stateful, and they store every item. Well, a given storage node, it's multi-tenant, and it's going to have a copy of the partition. That same copy is going to be on 2 other storage nodes. It's replicated 3 times. So let's see what the request path looks like. So let's say you're doing a put item request. That's going to land on, it's going to go through the network, resolve the DNS host name. You're going to land at a request router, which is, at the front end. There's technically a load balancer just in front of the request router, but we're going to include that under network. So request router is going to do a lot of things. It's going to verify your credentials, make sure you can access encryption key, make sure you have access to the thing that you're trying to access. And then, of course, it's going to figure out, and often it doesn't have to even look very far to figure out where the item should be written to. So the request router is going to look for what's called a leader. The leader, because we use a leader follower method. The replication algorithm is Paxos-like, Paxos. You're welcome to look that up, and I believe it's probably discussed in the DynamoDB whitepaper. So we're going to make sure that when we send that put item request to that storage node, which is responsible for that partition. Remember, a table is made up of 1 or more partitions, so partition's just really a shard of your data if you want to think about shards. We're going to make sure that it's durably written to 2 places before we acknowledge it. So we just need 2 acts, 2 successful writes. So you're sending it, to a request router. Request router is sending it to a storage node. That storage node is fanning out and sending it to 2 followers inside the replication group. And so long as 2 acknowledge it, well, usually it's the leader, which is, by the way, the one orchestrating this, right? Usually it's the leader that's going to write it first, and then it's going to get a response from one of the followers. And so long as the leader writes it and one of the followers writes it, they now have quorum, and the write succeeds, and you get a 200 OK back. Now, DynamoDB uses a leader election algorithm, which is Paxos-like. Now we have a leader election, and DynamoDB designates who this leader is by using a heartbeat protocol. And so each of the storage nodes participates in, participates in a membership group and heartbeats one another every 1.5 seconds. And if the leader heartbeat is not received, one of the other storage nodes will take over as leader, and one of the nodes with the latest version will be elected. So as you can imagine, what we're really talking about is there is a copy of data. It is in 3 places. if we durably store it in 2 before acknowledging it, it means that if we lose one node, well, there is still going to be one node running that has a copy of your data, and it talks to the other remaining nodes. So there's 2 nodes that are up and talking because the third one died somehow. And those 2 are going to talk about who has the most up-to-date copy of the data. And then, of course, they're going to be able to replicate the last bit of data to the storage node that's a little bit further behind. And then in that way, we can have 2 nodes that are available in the event of a worst-case scenario. And the great part about DynamoDB is so long as you have 2 storage nodes, the writes will succeed. Really interesting. Now let's talk about GetItem. Well, with GetItem, we're going to send a request to the network. It's going to make itself to a request router. And let's say you're doing a strong consistent read. So with a strong consistent read, we are going to find the storage node leader. So only one of the 3 copies of your data, one of the 3 replicas, one of the 3 copies of your partitions data, one of the 3 storage nodes. There's a lot of different ways to say the same thing, and each of those statements is essentially the same. Only one of those is going to be the leader. And so when you do a strong read, we're going to find that leader and retrieve the data. Now, if you request an eventually consistent read, which means you set consistent read to false, we're going to read a copy of the data. And it may be a little bit behind, on the order of microseconds and milliseconds behind. But it's really hard to say how far behind the third replica will be. It depends on a lot of scenarios that are outside of your control, potentially even seconds behind in the event of some kind of network dropout or failure. But usually these replicas are only milliseconds behind. Now, how do we pick which of these we're going to talk to? Well, for these eventually consistent reads, normally we're going to fetch the copy from the local availability zone. So if you're in, AZ1 in US East, we're going to talk, and you're talking to request router in AZ2. The AZ2 request router, if it has an eventually consistent read, is going to read the AZ2 storage node copy. It's going to go to the partition for that item key, that hash, and it's going to determine what the value of that item is and return it back to you. So there is an affinity between request routers where if you do an EC read, it's going to try to contact a storage node inside the same availability zone, aka data center, to get the item back to you as quickly as possible. Now let's talk about GSIs. So fundamentally, GSI is simply another table in DynamoDB, and the DynamoDB service asynchronously updates it for you using the log propagator service. Now, only items written to the base table that match the primary index are written to the GSI. Now note that if none of the selected projected attributes for GSI have changed, there is no write to be made and no capacity is consumed on the GSI. Your choice of attributes for the GSI primary key may result in a sparse index. Sparse index will come up later if you watch any of our design patterns talks. So anyways, the write consumption in a GSI can in some cases be lower than the base table. So let's say we need to make an update. So a GSI can consume more capacity than the write capacity on the base table. So let's say you change the value of the partition key. Let's say your partition key on a GSI was order status. The status went from new to in progress. I know this is a tired example, but everyone knows what it's like to shop online, I assume. So when you change the order status from new to in progress, we have to delete the old copy of the item. So that's a delete because that item is going to exist on one partition on the GSI. Then we have to insert it or put it to the new index partition. And so this means that when you're changing the values of the GSI partition keys, there's a bit of a write amplification. So you pay, if let's say your item was under 1K, because 1K is 1 WCU or write capacity unit in the provision mode. So it would cost you 1 WCU to update the item on the GSI plus 1 WCU to delete the old item plus 1 WCU to insert the item under the new, or sorry, technically in progress order status, because that is order status is your GSI partition key. So be aware of write amplification that can happen for GSIs. Now, let's go back. So why would it potentially be cheaper to do this? Let's go back 2 actually. So why would it be cheaper? Well, with GSIs, you can choose what the projections is. So you can choose all. This is a reminder. We kind of covered this earlier, but it can be, all or selected attributes, or keys only. And so if you have a smaller amount of data in your GSI, then the WC requirement is going to be lower, and so your costs are going to be lower. Now, there's also a service here on the side of DynamoDB, because this is kind of wrapping up the under the hood part, called AutoAdmin. AutoAdmin these days is like an automatic DBA for DynamoDB, and it does a lot of the value. Like it'll add storage nodes to replication groups. It will split partitions, repair partitions. It will handle provision capacity changes. It has some part in OnDemand. It's pretty cool. The AutoAdmin service is what allows the DynamoDB service team to manage thousands and thousands, tens of thousands. I can't even say how many thousands of servers. And it's going to allow you to experience DynamoDB, as much as it is possible as a serverless, highly available service with elastic scaling. And at this point with AutoAdmin, the sky is virtually the limit. And it's worth mentioning one more time that with DynamoDB, let's say for storage, you only pay for what you use. And for throughput, you pay for what you provision or what you use, in the latter case, in the on-demand mode, in the former case with the provision capacity mode. Now, let's talk about these two capacity modes and how we consume capacity. So now that you understand the architecture of DynamoDB, let's look at how to get the most out of the service. So our most common mode, I think even today, as of this recording, when you create a table with provision capacity mode, we're going to use auto scaling. You have the option to turn it on or off. But, we do have a new on-demand mode. We'll talk about that in a little bit. But auto scaling, it uses application auto scaling. You set your minimum and maximum capacity, which is how little or how much you want to spend. In addition, you set a target utilization. And so the service tries to keep your provision capacity, at 1 minus whatever your target utilization is. So let's say you're consuming, 70 WCUs. We're going to have the table provisioned for 100 WCUs. I don't know if I said that right earlier, but essentially the target utilization is, where we're trying to keep utilization as a percentage of your provision capacity. So let's look at this graph. This gives you a pretty good idea. So let's say you have a 70% target utilization. Auto scaling is going to scale up as your consumption increases and scale down as it drops down based on your target utilization. Now, the scale down is a little bit slower, as you can see, because that is based on whatever your target is minus, I believe, 20%. So if your target utilization is 70%, that means you have about 30% of headroom at any time. And then your scale down point would be about 50%. So it's a little bit slower to do that. So auto scaling is helping here because you only pay for the capacity you need. And it's also going to protect you in case there's any spike in traffic, because it has that extra headroom above your utilization. And it naturally prevents you from any kind of under-provisioning scenario. Now, let's talk about how DynamoDB tables consume capacity. At a high level, we have the desire to let you use as much capacity as possible, up to a set limit, which is 3,000 RCUs and 1,000 WCUs for a given DynamoDB item. Items sit on DynamoDB partitions. So let's talk about kind of the way that we handle this. So requests are admitted by the request router if there are tokens in the bucket for the table. So the table and burst buckets. We'll kind of talk through this here in a little bit. And so long as you have tokens at the top end in the table and burst buckets, or really whether you have the provision capacity in provision mode or if you're using on-demand, that's slightly different. But on-demand, we just want you to keep you under whatever your table throughput limit is. As long as you pass the upfront verification, we're going to send the request down to the storage nodes. And the storage nodes have their own view of the table. And so our target is 3,000 WCUs and 1,000 WCUs. So simply, you can think of it as a kind of two-stage check. Do we have enough provision capacity? Or if we don't have enough provision capacity, do we have burst capacity? Or in on-demand mode, do we have enough? Are we within our account limits? And if that is true, we push it down to the storage node layer. And then the storage nodes are going to check to see, are we going past 3,000 RCUs or 1,000 WCUs on the partition? And as long as all those check out, the data is going to come back. Now, step by step, here's how it actually goes. So that was the theory of it. Let's talk about the request path. Now, DynamoDB clients are going to send requests to the DynamoDB API endpoint in step 1. Okay. Now, step 2, this request is going to get routed to one of the many request routers in the region. Step 3, before the request gets handled, DynamoDB makes sure the permissions are in place to perform the request. Step 4, the request router needs to find the correct storage nodes relevant to the partition of the request by querying the partition metadata system. Next, we're going to check to see if the table has the capacity to handle the request, or in that case, we want to check to see if the table capacity is depleted. And if it is depleted, then we can try to use burst capacity, provided there's some tokens in there. Burst capacity is paid for, but unused capacity, which is equivalent to unused capacity from the previous 5-minute period. Or it's really just 5 minutes of unused capacity. It's not necessarily time bound, but that's a little too complex. Now, if you don't have provision capacity or burst capacity to get throttled, but if you do have one of those, the request will be delegated to the partition storage node. And right there at the storage node, it's going to look at the drive. It's actually taking some drive buckets, but it's going to look to see if you cross that threshold. So in the vast majority of requests, so long as you haven't exceeded 3,000 RCUs or 1,000 WCUs in that second. By the way, all of this is by second. You get that much capacity per second on partition. So as long as you have not exceeded that, the request will succeed. So. Now, we have on-demand capacity, and on-demand capacity takes a lot of the guesswork out of it. With on-demand, there's no planning for capacity. You just have your table limits, so like 40,000 WCUs, 40,000 RCU, or, it varies based on the region, but you can go look at what the throughput limits are, and that means that a single on-demand table can go up to that level of throughput. But there are some very important things to be aware of when that spike of traffic comes. So the key benefit is that you only pay for what you use. And so if you have a low utilization, you're not getting a lot out of your DynamoDB provision capacity because maybe you have spiky, unpredictable traffic, you can pay a little bit more because on-demand capacity does cost a little bit more, but you can end up saving money. We have plenty of customers who are able to save money with on-demand mode because although your capacity units are slightly higher, it's a higher cost per unit, you're able to use them more efficiently. Another benefit of on-demand is it's going to be able to instantly up to your count limit, say 40,000 WCUs, which is a soft limit. You can increase that at any time. It's going to be able to accommodate that spike in requests. Now, when you first create an on-demand table, it can go to 4,000 WCUs and 12,000 RCUs. This means if you work this math backwards, what we're saying is on-demand tables start with 4 partitions. However, you could start with the provision table and then switch it to on-demand. So if you knew you had an on-demand table, you need to go to 100,000 WCUs, make a provision table with that capacity, and then switch it to on-demand. Now, speaking of switching between the two capacity modes, you can switch to on-demand once per 24-hour period, and then you can leave it. So you can go from provision on demand once per 24-hour period. You can always check out. You can always go back to provision mode, but you can only switch to it once to on-demand mode once per day. So on-demand has this idea of twice your previous peak. So traffic can go up to twice your previous peak. Let's discuss what this means. So when you create a table, you're going to send traffic. The green light is requests. Whatever your peak is, we will look at that, and then we will add more partitions by splitting them. We will add new partitions, and that's going to give you more SSDs, memory, CPU, all that stuff that we discussed earlier with NoSQL databases. And that's going to increase your amount of capacity that you can spike to. So you set a new peak of traffic, and what DynamoDB does after, let's say, 30 to 60 minutes, because there is a bit of a delay, we'll add these partitions in, and you're able to go to high levels of request traffic. So put another way, if you have a table and you take it to a lot of requests and then it goes idle for a long time, then you have another spike in requests. The on-demand table will be able to hold that. We'll be able to satisfy and meet all those requests because the table, the whole service, adds partitions, but we don't remove them. It's just a fundamental part of DynamoDB. So on-demand, use it for unpredictable workloads. Use it for frequently idle workloads where you have really low utilization. Use it for use cases where you have unknown spikes in traffic, like you can't predict when it's going to happen, such as maybe a link being shared on the internet. Now, the provision mode is great when you have stable workloads. You have gradual ramps of traffic over tens of minutes. And it's really great when you have a lot of historical data of consumed capacity. So one thing to do is just be sure, just consider your tolerance for operational overhead and over provisioning. Because on-demand really is set it and forget it and is pretty great, but it does have its limits. So yeah. Now let's go ahead and talk about adaptive capacity. Essentially, what adaptive capacity does is sample your keys, and when it sees what could be a hot key, and it thinks it has a couple of models. that have been programmed, and it compares your access patterns to some of the models that it's been trained on, and it tries to make a decision: would this partition benefit from a split? Should we put this key on its own partition? So imagine partition A, you have item foo and item bar. And let's say we're starting to see a lot of requests to item foo. So what DynamoDB can do is begin with splits. And so through splits, it can say, okay, now we have two partitions and foo is off there on its own. And then eventually we can go all the way down and isolate item foo to its own partition. Now, we see partition A and B, item foo is on a partition that really should say partition C. We'll fix this PowerPoint later on. But the idea is that with adaptive capacity, we can what's called split for heat. And so you're going to take a single partition to 3000 RCUs, really a single item to 3000 RCUs and 1000 WCUs. And then the DynamoDB service will do this for you automatically, redistributing your traffic. Now, AWS, in this case, is literally adjusting our service to fit your usage patterns. And so this can ultimately result in a single item on a single partition, which is pretty amazing. Now, the one thing is, this is a value add feature. This happens underneath the surface, so you're not going to have a lot of insight into whether this is happening. So sometimes you have these hot keys, right? And you may not know what they are. And so instead of waiting for adaptive capacity with split for heat to kick in, let's sample our keys and figure out which keys are hot. And that's where CloudWatch Contributor Insights for DynamoDB comes in. CloudWatch Contributor Insights for DynamoDB creates 4 different graphs. You have the throttles and the admits. So the admits are the most access keys. The throttles are the most throttled keys. And then we do that for both partition keys and sort keys. So as you can see this graph, you can see which items are getting the most requests, and this is great. Now, there is a cost for enabling it, and as soon as you disable it, by the way, the data does disappear from the DynamoDB management console. But this is a great way to find any kind of hotkeys you have. If you get some throttling, you can turn this on while it's happening and identify what the keys are. As a solutions architect, this is great as well because you have a schema. You tell the engineers what the schema should be. How do you know if it's been implemented? Well, you can actually use this. Maybe you're doing some perf testing and you just have some non-unique partition keys. Maybe that's why you're getting throttling. This gives you all the insights you need to figure out what is the data that's being read and written. Now, be aware this is, I think it might be, check our documentation. I think it might be encrypted in CloudWatch Contributor Insights, but we are sending your partition key values to this other service. So hopefully your company will allow that and approve it. And do check your security requirements. Now, every service, whether it's DynamoDB or CloudWatch, we have detailed documentation on security. We're very transparent on how data is handled, encrypted. Wherever possible, we allow you to use your own account customer managed key. Security is the #1 priority at AWS. So I just want to emphasize that you are in control of your data. You're in control of whether it goes to CloudWatch Contributor Insights for DynamoDB or not. So if you have specific security requirements, please do check our documentation. Now, speaking of features and security and all these great things in Dynamo, as I said earlier, if there's a feature you're looking for, we probably have it. We have import and export. We have ACID compliant transactions. We have a tool called Nosql Workbench, which is the SQL developer friendly tools, or SQL friendly developer tools, that is. We have all kinds of integrations with other services. Like, for example, if you want to read or write data on DynamoDB, you have to use AWS IAM policies. One of the new features I want to highlight is our table classes. So we have SIA, Standard Infrequent Access Table Classes. So with SIA, you pay a lower cost for bytes for storage. That is the timed byte storage hours. This is the data stored on SSDs. So it's a lower cost, with the trade-off being a slightly higher cost for read and write units. So the rule of thumb is that if your storage costs are more than half of your cost for capacity, for throughput, for reads and writes, then you should consider using SIA. Now, one of the most common misconceptions is that standard IA is a different performance tier, and it is not. It's exactly the same DynamoDB, the same latency, low latency, high availability. It really is amazing. So consider using standard IA table class when you have a storage cost for timed byte storage hours, is basically your bytes on disk, where that total cost is more than 50% of your cost for throughput, reads and writes for your DynamoDB table. Now, be aware, SIA is not available, or sorry, not compatible with reserved capacity. So if you purchase reserved capacity reservations in 1 or 3 year terms, those will not apply to SIA tables. So we are here at the end of our presentation. Thank you so much for learning about DynamoDB. There is a new paradigm. You need to use the right database for the right job, and NoSQL databases are very powerful. So if you have a mission-critical OLTP use case, consider using DynamoDB. NoSQL databases scale horizontally by adding nodes, and that's a really good thing. And really, you want to go with something that has a long track record, more than 10 years of operational history, that's trusted by companies that you use every day. That runs everything from, video streaming services, to, in some cases, to credit card transactions. And as you come to use DynamoDB as a NoSQL database, it's really important to model the relationships and use these things called aggregates. So please look for other content, learn about how to model for NoSQL designs, because if you get a really good schema, you can operate at scale. And so trust DynamoDB, a fully managed service, is enterprise ready to run your applications. And so with that, thank you so much. Have a good day.